A gamma-ray burst releases more energy in a few seconds than the Sun will emit across its entire 10 billion year lifetime. Let me say that again precisely. Not more than the Sun emits in a year, not in a million years, in its entire 10 billion year existence. Every photon, every particle, every watt of solar output, from ignition to final cooling, a gamma-ray burst matches or exceeds that in the time it takes to read this sentence. And it doesn't radiate in all directions, it beams, a narrow jet of gamma radiation moving at nearly the speed of light, aimed at whatever is unfortunate enough to be in its path. If one of these were pointed at Earth from within a few thousand light years, complex life on this planet would likely end, not in centuries, not in decades, but through a cascade that begins in seconds and plays out over years, starting with the destruction of the very layer of atmosphere that makes the surface habitable. I'm Paul Dirac. Let's understand what these things actually are, how they work, and what they mean for the question of why the universe seems so quiet. There are two distinct types of gamma-ray bursts, and both are extreme in ways that deserve precision rather than vague description. Long-duration GRBs last more than 2 seconds, sometimes minutes, and are produced when a massive, rapidly rotating star collapses. As the core implodes into a black hole or neutron star, the infalling material forms an accretion disk, and the intense magnetic fields and angular momentum launch a jet, a relativistic outflow of plasma and radiation that punches through the stellar envelope and fires into space at close to the speed of light. The dying star becomes a weapon. Short-duration GRBs last less than 2 seconds and come from the merger of compact objects, 2 neutron stars or a neutron star and a black hole, spiraling together over millions of years before finally coalescing in a catastrophic collision. The 2017 event GW170817 confirmed this directly. A neutron-star merger detected simultaneously in gravitational waves by LIGO and in gamma rays and optical light by telescopes worldwide. The merger, the GRB, the kilonova, all observed in real time across multiple channels of information. One event, multiple messengers. The confirmation was definitive. Both types produce jets of gamma radiation. Both are the most energetic explosions in the observable universe. The phrase gamma-ray burst sounds clinical. It substantially undersells what's happening. Now the numbers, because the numbers are where intuition breaks. The peak luminosity of a gamma-ray burst, the brightness at its most intense moment, can equal the combined light output of every star in the observable universe. Every star in the observable universe, simultaneously for a fraction of a second. This isn't hyperbole, it's a measured quantity from detected events, calculated from the brightness and distance. The total isotropic equivalent energy, the energy you'd calculate if you assume the burst radiated equally in all directions, can reach 10 to the power of 47 joules. The Sun's entire lifetime energy output is about 10 to the 44th power joules. A gamma-ray burst releases in seconds what 1,000 suns couldn't produce in a billion years. These numbers aren't just large, they're outside the scale human intuition was built for. They require a different category of thinking, not very powerful, but a different class of phenomenon entirely. Now the jet, because the geometry changes everything. The energy isn't radiated spherically, it's collimated into narrow cones, typically spanning just a few degrees of solid angle. This has two consequences. First, the true total energy is lower than the isotropic equivalent suggests. When you correct for the beaming, a GRB's actual energy output is closer to 10 to the 44th power joules, comparable to a supernova's total energy output, extraordinary but not universe output level. The apparent brightness was amplified by the beaming. Second consequence, and this is the one that matters for us, if you're in the jet's path, you receive a radiation intensity that spherical emission at the same total energy could never produce. The same energy focused into a few degrees of sky versus spread over the full sphere, the intensity in the jet direction is orders of magnitude higher. We only detect GRBs when their jets point toward Earth. The ones whose jets sweep in other directions we never see. The galaxy is being traversed by these beams continuously in all directions, and we observe only the fraction that happen to aim at us. Most GRBs are invisible to us, their jets firing silently through regions of space with nothing to illuminate. Now, what actually happens to a planet in the path? For a GRB within a few thousand light years, aimed at Earth, the mechanism of destruction is indirect, and the indirection is key to understanding why it's so effective. The gamma-ray photons aren't primarily killing organisms directly. Most of the surface is shielded by the atmosphere from direct gamma exposure. What they're doing is destroying the ozone layer. When gamma rays arrive at Earth's upper atmosphere, they interact with nitrogen and oxygen molecules, producing nitrogen oxides, reactive compounds that catalytically destroy ozone. A single nitrogen oxide molecule can destroy many ozone molecules in a chain reaction before it's removed from the atmosphere. The result, within seconds to minutes of the burst arriving, significant fractions of the ozone layer are depleted. Estimates vary, depending on the burst intensity and duration, but ozone depletion of 25 to 50% or more is plausible for a burst at a few thousand light years. The ozone layer is what blocks most of the sun's ultraviolet radiation from reaching the surface. Without it, UV flux at ground level increases dramatically. UV radiation destroys DNA efficiently. It causes mutations, kills microorganisms, suppresses immune systems, and at high enough intensities, kills outright. The most vulnerable? Phytoplankton in the upper ocean, which form the base of the marine food chain, and land plants whose surface tissues are exposed to direct sunlight. When phytoplankton die en masse, the food chain built on them collapses. Marine ecosystems fail from the base. Land ecosystems follow. The GRB itself lasts seconds. The ozone depletion persists for years. The extinction cascade plays out over decades. The burst is the trigger. The UV exposure is the extended weapon. Here's where history becomes relevant and uncomfortable. 445 million years ago, the Late Ordovician mass extinction eliminated roughly 85% of marine species. It's the second largest extinction event in the fossil record. The cause has been debated for a long time. The geological signature includes evidence of rapid cooling, glaciation, and, here's the telling detail, patterns of extinction that preferentially affected organisms in shallow sunlit waters where UV exposure would be most intense. Species in deep water, shielded from UV, survived at higher rates. In 2004, astrophysicists Adrian Mellott and Brian Thomas published a paper proposing that a gamma-ray burst within roughly 6,000 light-years of Earth could explain this pattern. The preferential loss of UV-sensitive shallow water organisms, the rapid onset, the ozone depletion signature. This hypothesis isn't confirmed. There's no smoking gun, no GRB remnant we can point to. The fossil record doesn't preserve the burst itself. But the hypothesis is scientifically serious. It hasn't been dismissed. And it raises a genuinely strange possibility that Earth has already been hit, that the late Ordovician mass extinction, 85% of species gone, may have been caused by an event lasting seconds, 445 million years ago, from a dying star whose name we'll never know. And life recovered, rebuilt, diversified, eventually produced us. Now, where you are in a galaxy matters. GRBs are associated with star-forming regions, places where massive, short-lived stars are abundant. The galactic center has a high star formation rate and high stellar density. It's more GRB active. The outer regions of galaxies are quieter. Metallicity, the abundance of heavy elements, suppresses long GRBs. Low metallicity environments are more prone to them, because massive stars in low metallicity environments retain more angular momentum, producing the rapid rotation needed for GRB jets. The early universe was low metallicity. GRB rates in the early universe were substantially higher than today. Life trying to establish itself on early universe planets faced a much more violent radiation environment. Repeated sterilization may have been common, not a single extinction, but cycling. Life begins, reaches some complexity, a GRB resets it. Begin again. The Milky Way today, in its outer regions where we live, is relatively high metallicity. Long GRBs are suppressed here. We may inhabit, by the luck of cosmic location and epoch, one of the safer environments the galaxy offers. Not safe, safer, and we can't predict them. This is the part that doesn't have a reassuring resolution. GRBs are detected after they've begun. The burst itself is the first signal. There are no reliable, identifiable precursors. The progenitor systems can sometimes be catalogued. Known neutron star binaries, massive stars approaching the end of their lives. But the timing of collapse or merger is not predictable with useful precision. A neutron star binary might merge in 1,000,000 years, or in 1,000 years, or in a century. We don't know. We can't know with current understanding. The catalogue of neutron star binaries in the Milky Way is incomplete. Short GRBs from mergers remain possible. Our current relative safety from long GRBs due to metallicity is a statistical tendency, not a guarantee. The warning time when a GRB fires in our direction is 0. The burst travels at the speed of light. There is no pre-signal. The first indication would be the gamma rays arriving, and this brings us to the Fermi paradox, the question that GRBs make considerably darker. The universe is 13.8 billion years old. In that time, by the most optimistic estimates, there should have been enough time for intelligent life to arise, spread, and make its presence obvious across the galaxy. We see no sign of it. The sky is silent. Where is everyone? GRBs offer one answer. A serious, quantitative, physically grounded answer. If GRBs have been functioning as a recurring, unpredictable sterilization mechanism across the galaxy, especially in the early high GRB rate universe, then complex life may have been repeatedly reset, not once per planet, but many times. Life gets started, survives for hundreds of millions of years, approaches complexity, a GRB fires, the biosphere is set back, perhaps not to zero, but far enough to require millions of years of recovery. By the time it reaches complexity again, another burst, the experiment resets. We are here because in our specific location in the galaxy, at this specific period in galactic history, the GRB rate is low enough that life had enough consecutive, uninterrupted time to reach complexity, or because a past GRB hit us, the Ordovician suggests this possibility, and life was robust enough to survive and rebuild. The survivors of that extinction carried life forward. We are their descendants. The silence of the universe might not reflect an absence of life. It might reflect a universe that regularly, efficiently, invisibly resets the civilizational clock, with events lasting seconds, beamed from dying stars, carrying no warning signal, and leaving nothing behind but altered atmospheres, collapsed food chains, and the long, patient rebuilding of ecosystems that were just, finally, getting somewhere. And somewhere in the galaxy, right now, a massive star is collapsing. A jet is forming. It will fire in some direction. Most directions, nothing in the way, or nothing close enough to matter. But one direction is Earth. The probability that it's aimed at us is small. The probability isn't zero. That's the most honest thing physics can tell you about it.